science principles with fun all over the country and has set up over 35 so far. So very, interesting and so very impressive, sir. So I would request Professor Vijay now to start talking about the, very, very interesting topic he has chosen. Over to you, sir.
Yes, good morning, madam. And I'm really happy to see large number of participants in this program. I hope you are able to see me.
Yes, yes, we are able to see you, sir.
Okay, and I take you around the lab where I'm working right now. It's a school of the 12th standard, and we have set up the innovation hub here. Okay, and what you can see is this IAS University, which has set up this Center for Innovation in Science Teaching. Okay, CIST we call it. And I'm looking after the activities here, how to improve the science teaching in the classes at UG and PG level as well as the schools. So, well, this is a laboratory where all the innovative projects are kept. Innovative projects means there is, of course, a conventional laboratory with the optical bench, potentiometer, and other galvanometer, ammeter, physical balance. Okay, so along with the conventional lab, we have got an innovative science lab where most of the experiments are designed and developed using low-cost material, locally available material, like there is a tube of car over which in which water is filled, and when you ride on it, okay, the water level changes, and with the change in water level, you get idea of measurement of your weight. You can measure your weight with couple of pendulums mounted here, okay, with varying length. You can get a feel of phase relationship amongst each other when you move them together, okay. Using these bicycle part, we can make rotational dynamics experiment, okay, and talk about the escape velocity, centrifugal force, and so on, using the speaker and the metallic strips. We can talk about the waves in a circular path. We call it as a Bohr orbitals. Okay, using such a drum, we can show how this air cannon works. There is a screen, and when you hit this drum, the impulse goes. So you listen the sound. Sound travels very fast, but the impulse goes slowly to the top. Okay. We have got an air track, and on air track, this moving object can move without friction when we blow air from here. This moving object
Professor Vijay, it will be better if some other person holds the video for you. and you can show it, because it is sometimes going out of focus. Yeah. Yes.
So because of this magnetic interaction, the glider, because of the magnetic interaction, the glider moves on this triangular air track, okay, in a straight line, and there is no friction. We've got a vacuum chamber to show the plasma state, fourth state of matter. We've got a water tub to show the waves on the surface of water. So when you have a reflected light going to the roof and you disturb the surface of water, then you see the wave propagation.
That's beautiful.
Okay. And this is the arrangement. On a water tray, you normally don't see the surface waves, but with the reflection, you can see it and show it to the whole image.
So for all these experiments are set up into all the innovation hubs throughout the country?
Yes. All these experiments, about 30, are set up in innovation hubs at different part of the country. So we've got an experiment on sound using such tube. We've got experiment on eddy currents using such a device. So you connect to the electricity.
It's going out of focus, sir.
Yeah. You see.
Okay.
Wow.
So
Very
this
And
shows
sir,
the magnetic levitation.
okay.
Right?
Yeah.
As you power this coil, so these aluminum bangles, they are lifted up because of the varying magnetic field, because the alternating current is flowing in this wire. And this is the coil, and there are iron pieces. Okay.
Yes.
So most of these models are made using the low cost material. Okay. Easily available anywhere, and they can be easily duplicated. All right. Like these floating magnets, I will be talking about how they can arrange themselves. Okay, very nice pentagon pattern. Right? If I remove this, then they will be having an equidistance configuration, and nothing but a ring magnet is attached to the bottom of one of the plastic ball, and all of them are set automatically on the water surface. Okay.
Sir, the camera a little bit towards left, please. Yeah. Now we can see the whole container. Yes.
Yeah, correct.
Okay.
Yeah. So this is how most of the models are designed and developed. Okay. And it's all the IIPT platform which we are using to share these models. And then once they are perfect, reproducible, then we take it to different institution. Okay. I show you another one.
And sir,
Right.
what you mean to say is that such an innovation hub can be set up in any institute, whoever is willing to invest a little bit of space and a little bit of money for the setting up of this innovation hub within the institute. So any school or college can do it, isn't it, sir?
Can do it, yeah. And it's very useful to learn and see the fundamental phenomena. For example, this shows a coupled oscillator system. Okay, how the molecule behaves. All right. So if one of the atom gets disturbed, it automatically transfers energy to the second one.
Sir,
And back
very
to
nice.
Sir, who is funding these projects?
Nobody is funding, ma'am. The
Nobody
institute
is
has to
funding.
fund.
You have to fund. Okay, we have
Oh,
designed and developed and made a collection of them. Okay, and a lot of literature has been developed. So that comes with these models. And one private vendor is duplicating these models for us. For example, these couple oscillations, you have using these balls, crazy balls. Okay. So most of them are low-cost propositions, low-cost models, okay, which are designed in such a way that they can be maintained in any laboratory.
So, sir, may I ask approximately how much money is needed for setting up a lab of this kind in one institute?
Approximately 2 lakh rupees
2
is
lakhs.
needed.
Okay.
And some area of space is also required within the institute, school or college.
Yeah, area is approximately 600 to 800 square feet.
600 to 800 square feet.
So this shows an open CRO. Okay, you are having a
Wow.
LED light with a lens and a screen. Okay, and if I have a moment of only one pendulum here, this pendulum, then the spot is not moving. If I disturb one pendulum, then the spot moves. So this shows a movement along x-axis in a CRO. And this shows the movement along y-axis on a CRO. And if both of them are moving, then you get the Lissajous figure, depending upon the phase. So it's a elliptical motion.
This is actually marvelous, sir, that how we taught them by drawing the picture of CRO on the board that this is the magnetic field, and now it is all in front of them. How Lissajous figures are
it's all mechanical. Okay.
Varsha, on CRO we show it, but in a mechanical form, this is really interesting. I mean,
Yes.
we do see
Yes.
sideways and show them the Lissajous figures, but this
Yes.
is excellent because this is, more physics goes into it.
Yes,
Yes.
ma'am.
I mean, I personally think that such experiments should be there mandatorily in every undergraduate laboratory.
Yes, exactly.
I frankly think that they should be there with every institute.
Yeah,
And 2 lakh rupees is not
rather
really
than
a huge amount of money.
rather than having the closed boxes,
Yes, exactly.
we should have an open platform where we can visualize each and every part of it and then play with it. Okay.
Yes.
That is the theme. Okay. So normally we bring students here, all right, without assigning them any question paper or any theory topic. Whatever they see, then the question comes out of those. So, well, in normally physics or chemistry, you start with the nature and talk about the motion of ball, motion of planets, and so on. Okay. But here, all these fundamental phenomena are taken systematically with some specific geometry so that the vocabulary is visible. For example, the wave is traveling, so you can see the traveling wave, and getting reflected, you can see the getting reflected wave coming back. Okay, so the parameters are chosen in such a way so that they come in the visible range. So the wave propagation, the longitudinal wave, transverse wave, and the torsional wave, all these concepts come together. Not only the static, but rotational dynamics, the lift, the pulley system, okay. And along with that, I will be talking about the quantum phenomena that also comes in the visible range. Okay. So I will switch over to my laptop and show the presentation systematically for the benefit of all the participants. Is that okay? So this is a tour to Innovation Hub right now. Okay. And the Innovation Hub has got scientific principles in all these experiments. Okay. Like the friction. The friction is because of the atomic interaction. Okay. The pendulum motion is because of the gravitational potential. The Lissajous figure are because of the phase relationship between the motion. Okay. So all these concepts which are brought in visible range, we say that the quantum phenomena which occurs in nature in the quantum world, okay, all the van der Waals forces, Rutherford scattering, potential well, all these things can be brought in the visible range using the gravitational interaction and a magnetic interaction. Okay, and that is what we have converted in the form of innovative science models. All right.
Wonderful, sir. It is, you've got a mini national science center within your innovation hub. And sir,
yes, exactly.
At how many places or how many institutes? 13 you said, but where in India have they set up these innovation labs?
You can get a list on a website, IIPT website. Okay. Yes. And all these innovation hubs are distributed all over the country. Right? Like one is there in Bhubaneswar, one is at ISR Calcutta, then Himachal, Punjab, Gujarat, Maharashtra. Okay, so all these places, the list is there. So 38 have come up so far.
Oh my God!
Right?
Oh my God!
All over the country, and we are in the process of taking it to Patiala, and another one is coming at Rajkot soon. Okay.
So in Patiala, apart from Patiala, is it available anywhere else in Punjab?
Punjab, Batinda is available at DAV College, Batinda.
Which institute, sir? Which institute in Batinda?
Batinda, it's a DAV college. DAV College, Batinda.
That answers the question of one of the participants. Where is it in Punjab? Sir, another participant asks, how about assigning to build a physical model as a project to students and providing assistance to the students?
Okay. What we feel is few parameters are already explored in most of these projects so that it is measurable. But the variation in those parameters can be done in the form of student projects. So all these laboratory experiments, when they perform in the laboratory, okay, they can vary the parameter. For example, this one. Okay, they want to change the weight of this and see the dynamics, they can do it. How to add weight, this is their innovation. Okay, they can stick coins here, 1 coin, 2 coin, 3 coin, and how the coefficient of friction is changing by changing the load. So this becomes a quantitative project for individual students. Okay.
Okay.
The
next one should be somewhere in Delhi for us.
Yes, I was also about to say the same thing, the Delhi NCR region, where we can also see.
Yes. In Indore also recently, SV University, Indore, okay, Sri Vaishnav Vidyapith University, they have set up an innovation hub with all these models there. Okay. And where they have started interacting with the students. Okay. For example, this model, we gave only one loop as a Bohr orbital model, but student wanted to have the multiple loops. So in the same speaker, the multiple loops are mounted. And then again, study the resonance states of these multiple loops. Because in a Bohr atomic model, it's a single loop concept. The single orbital concept is used, 2 pi r equal to n lambda. But there are different loops. So r is different. Then the quantization condition for different loops will be different. And your driver is driving at a particular frequency. So only one particular loop will be excited, other loop will not be excited. So such concepts, which are a little advanced concept, they can be introduced as a projects. Okay. So there are many more projects like on electrical network analysis, okay, using these choke, valve, and capacitors to study the LCR circuits, and also using a TC arrangement on a valve, okay, we can measure resistance of valve when it is glowing, the dynamic resistance we call it, okay. So such innovative projects can be introduced within the laboratory once you are open. You are having a open-ended experiments. And this plasma chamber, you can introduce different gases and study the plasma characteristic of different gases. Here, the exciting voltage is also variable, all right? So that you can excite the plasma at different voltages, okay? So these are some of the themes over which we have been working, because I was with the University of Rajasthan and with Professor Babulal Saraf and Professor D.P. Khandelwal. Okay, I spent time and learned variety of pedagogy methods which we can use, okay, and share with the students. All right. So all these are basically the journey which has come out. And now,
amazing, sir, amazing. I think
when you are ready to share with the next generation, okay, you have to work in the low cost mode so that it can go to everyone.
Yes, yes, yes. Okay. That's very true. Somebody asked how they can set up such a innovation hub, and I've replied from your side that they can contact you directly and you will explain how they will, how you will come with your team to their institute, school, college, or whatever it is, and set it up.
But we go there. Yes. With all these,
they have to provide you space, as I understood correctly. They have to provide you space, and they must have a funding of around 2 lakh rupees for this all these experiments to be set up. And then they have to learn how to conduct these, and they can go on with the conduction of the experiments. Am I correct, sir?
Yes, exactly.
Thank you.
We give them a 1 or 2 day training on all these experiments with all this literature, and they are all open-ended experiments. Okay, so they can do a lot of modification and redo these projects for their better learning. Okay, continuous, because learning is a continuous process. Once you have some model, all right, you can continue to innovate in that, add on, okay, and do more and more. All right.
Very true, sir. Open-ended experiments are are much better for the understanding of the student rather than dictated aim and specified observation table and specified expected graph which the student tries to obtain by this way or that way. So open-ended experiments are really nice.
Most of the material which is commonly available in the market, because when you want to extend any project, okay, then the material should be easily available. For example, you want to work with the valve, electrical valve, and study the dynamic resistance of a valve. Okay, what material the valve is made of, So you want to study the temperature variation, the coefficient of temperature variation of a bulb. Okay. So you can buy different bulbs from different company. Philips is available, Bajaj is available, Surya is available. Okay. Is everybody using the same material? Okay. So these questions you can answer while you are doing these projects. Okay. Because your setup is here to measure the resistance, dynamic resistance of a bulb. Okay. So you can use 100-watt bulb, 40-watt bulb, 60-watt bulb, and establish your relationship. Okay. And that's how it should go. So I had to switch off my mobile for going into the laptop. So there may be a 1 or 2 minute interruption. Okay. You will be more comfortable. Yeah.
Yes, sir.
Okay.
No problem, sir. Thank you so much, sir.
Thank
We'll
you.
wait.
I
We'll wait.
leave, otherwise there will be a cross noise, you know.
Yes,
So
sir.
I leave this meeting right now and join the other. Okay.
So one of the participants, Dr. Sanjay Kumar, writes that he has this facility in SD College, Barnala, made along with Professor Vijay, sir. So Dr. Sanjay Singh is present in our meeting, sir, and he says that you have motivated him a lot.
Okay.
And that is really good. I personally feel that there are many students whose visual extrapolation or interpolation faculty is not that much developed. And a lot of time is wasted in the classroom in trying to pick up those students to the same level where they can visualize a particular concept in physics. So even though these experiments are very simple to look at, for at least 30% of the students, this is very, very inspiring, motivating, and it is helping them to catch the concept. I have noticed that students sometimes are not able to even contemplate the idea of a wave in reality, you know, and we keep on drawing them, and especially from optics. For example, what they see in a book while studying diffraction and interference, the kind of things that are written in their college books or school books. And when they perform the experiment in the laboratory, two things are widely different, and some of the students really can't correlate. So these experiments would be very helpful in understanding. And another bottleneck is the moment we start with modern physics, the concept of wave-particle duality, which is a very base of quantum mechanics, is just not understood clearly. The atomic model is the Bohr atom model, which is the base of everything to start with in modern physics.
The quantization
is not clear at all. Is not clear at all. And sometimes, unfortunately, even in the third year, we are repeating that concept again and again, that if you cannot catch Bohr atomic model and wave particle duality, you cannot really understand nuclear physics and particle physics and so on. So I think it would be wonderful, even if the model is not an exact replica of the concept, it will be very beneficial to them. Sir, have you connected to your laptop? I was just filling in.
Yeah. Okay. Yeah, I'm with the laptop now, and
there is some echo, sir. You have.
Yeah, I will switch off the mobile. Okay.
Yeah. Okay. Yes. Yes.
Good.
Sir, would you be sharing your screen or?
Sure. I will share my presentation.
Sir, it is still echoing. You have to log out from that device completely, or leave it in some other room next door.
Okay. Let me log it out.
Meanwhile, if the participants have any question, they can put it on the chat box. And I would like to announce again, Indian Association for Physics Teachers is a body of all physics teachers all over India, and everybody participates in it willingly. You can take a membership of Indian Association of Physics Teachers by visiting its website and learn continuously with the very learned, respected teachers all over India who are connected with it and its regular activities. And NASI helps us propagate science through society in each and every way. And that is why we are thankful to NASI to have supported this particular webinar series, so that the good work of the physicists of our country reaches everybody. So anybody who is not a member of IIPT should try to become a member of IIPT. It's very, very beneficial. Yes, sir. Yes, sir. You are now.
Yes, sir. I'm ready to share.
Please,
okay.
sir.
Is it visible?
No, sir. No, not yet, sir.
Not yet. Not yet. Okay. Okay.
IPT also holds examinations for undergraduate students. BSc second year and third year students are eligible to participate in that examination, which is held all over India on the third Sunday of every year. So third Sunday of January every year, IPT holds examination for the undergraduate students and makes them realize where do they stand as far as physics is concerned. So there is a green button down there that shares screen.
Yeah. So you are having a disable on that.
Okay, sir. Just a sec.
Make it
I'll
enable.
have to. Sir, just a sec. So this is the other device. I'm not able to make you but I had made you a host, sir. Can you see yourself as a, sir? Can you see yourself as a co-host in this? Varsha,
Yes, ma'am.
please make Yogesh sir's second device, the laptop, as co-host. Only then he'll be able to share. Yes.
So please try now.
So please try now.
Okay. Yeah. Good.
Okay.
Is it visible?
Sir, it's coming. Yeah.
Okay.
Science for everyone.
Science for everyone. Good. Okay. Let me. Yeah. So I'm in Science for Everyone, the theme I shared. And the motivation is you should learn science while playing. Okay. Then it is yours. Okay. If you learn science only by mugging for cracking exam, then it is not yours. You forget after some time. Okay. So you have to play with it. Then it is yours. It stays with you. This is the theme I'm talking about. Well, in fact, all this is dedicated to our great quantum physicist of India, C.V. Raman. He talks about interaction of photon with atom. Okay, how the energy of the photon changes while it is interacting with atoms. Meghnad Shah talks about basically how the light is originated from atoms. Okay, the light coming from sun, light coming from star. So he talked about the thermal ionization. Everybody, most of the material, quantum material at high temperature, they start radiating light. Okay, and that is what we acknowledge Meghnad Shah's contribution. And S.N. Bose's contribution is how these atoms and molecules exchange their energy. So we talk about the Bose-Einstein statistics and so on. And his basic work is acknowledgement all around. So everywhere in physical world, we talk about parallel quantum world, where the atoms, molecules, photons, electrons, these are there, and how they are exchanging their energy, how they are interacting, what are different energy states and so on. Okay, and that is what we talk about, and how we can learn from the quantum world to the physical world, how they are connected. Okay, this is what I like to share. So this tour I have already taken you. Quickly, if you have got a time, I can repeat or I can skip. You already know what is this. Okay, well, we also dedicate all this theme in the centenary year of Professor D.P. Khandelwal. Okay, he has been inspiration for IIPT. He used to stress about the quality of education, quality education, and he used to stress upon physics through experiment. Okay, because physics can be understood, can be brought home through experiment while doing. He initially set up throughout the country for Center for Science Culture. Okay, but now the same theme we are upgrading to innovation hubs, and so far only one science center, Midnapur, is surviving, although Professor D.P. Khandelwal initiated 4 science centers in the country. Okay, but now we are talking about the innovation hub, and throughout the country there are about 38 places innovation hub are in function. They are functional. All right. One of the innovation hub I can take you around at Una, Himachal. Okay, this is how it looks like. A video clip, 2 minutes video clip to give you a glance how the new innovation hub looks like. So they have set up a laboratory about 800 square feet, 20 by 40, and they provided us tables and electrical points, and we carried most of these equipment designed and developed here along with the literature, and these are installed there, and they are staying there permanently. Students and teachers can visit. Okay, and this is how the innovation hub looks like. An independent place of learning. There are no experimental records. Okay, there are no examination, but you just play with them and learn the fundamental science. Okay, while doing. So I'll be talking about some of these models. Okay, how do we extract science out of these models? Okay, particularly the phenomena of quantum mechanics, which comes in the visible range, I will be talking about through some of these models. Okay, not all. But this is how broadly most of the innovation hub looks like, and most of these models are duplicated. So you can see air cannon is also there, electromagnetic induction is also there, the rolling dynamics, rotational dynamics, the Bohr orbitals, or the atomic vibration. Okay, all these models are duplicated at different places. Okay, and stored, so the student can sit, relax, and enjoy. All right, the angular momentum, the lift, all these concepts are installed there. This is measure your weight again. Okay, the same which I showed you here. This is a vortex formation, black hole dynamics, wave apparatus. So all these are duplicated and installed there, and they stay there. Okay, this is what we feel is a IIPT's contribution countrywide. So what I will be talking about is atomic configuration, how the atom arrange themselves. What are the van der Waals potential? Okay, interaction between atoms and molecules is van der Waals force. The lattice potential I will be talking about, how the electron is moving periodically, meeting different atoms. Okay, I will be talking about the Rutherford scattering, Bohr orbitals, Raman effect, alpha decay, molecular vibration, plasma state, bouncing laser. All these are bought in the visible range. When you do things in the laboratory, things are visible. Okay, all these words will be translated. These are all quantum words. Okay, and these will be translated into visible models. For example, this atomic configuration. This is a hexagon symmetry. This is how the atoms are arranged, because the atoms are spherical. How the atom interact? They interact through van der Waals potential. Okay, van der Waals potential is attractive as well as repulsive, and they come in equilibrium at a certain distance, where the attraction and repulsion is balanced. And this is the equilibrium configuration. Okay, it's dynamical. You can play.
Are you speaking something?
Huh?
So there is no sound in the video, na?
No, there is a sound in the video. Is
But
it audible?
No, it's not audible because you have not shared you have not
Oh,
picked the small
okay,
button,
okay.
share the sound.
Oh, I see. Well, what it is describing is atomic configuration, as I said. Okay, these are floating dipoles. All right, they arrange themselves on a surface of water. Equidistance. When the number of balls are small, they are far apart. When they are large, they are compact and closely packed. Okay. Can I switch to the audio? Can
Sir,
I?
from wherever you are sharing this,
Okay.
before you share the video, there is a small box below it which says share computer sound. That has to be tick marked yes.
Okay. Sharing the green button.
Uh, not just the green. Sir, you're already sharing your PPT slide.
Yeah.
So while sharing, you should have clicked the share computer sound button before you started.
Okay.
So maybe you
So
stop
I have to
sharing and
redo.
share again. You have to
Okay.
stop and
Okay. I stop sharing
yes, sir.
and then share again.
Yes, sir.
Share again.
And
Okay.
while you share, there is a small button towards left-hand side corner which says share computer sounds.
Share sound. Okay.
Yes, computer sounds. Yes, yes. So the video that is embedded will play now with sound.
Okay. All right. Let me try again. In order to show atomic configuration, we have got a model in which the ring magnet is attached on each ball with identical polarity of north-south, so that the dipoles are interacting. The balls are able to float on a surface of water, and they arrange themselves in a particular configuration. 7 ball with hexagon symmetry, 5 ball or 6 ball with pentagon symmetry, and when there are 4, they result into a cubic symmetry. If there are only 3 balls, they are having a triangular configuration. So the atomic configuration is also similar to the spherical atoms, having interaction, van der Waals interaction, and organize themselves in different pattern when they are repelling each other. So, well, let me take you to the next model where we talk about the defects in solids. Okay, the atoms are arranged. If they are arranged in a systematic way, then we call them a crystal. If they are not arranged in a systematic way, then there are defects, amorphous. Okay, and this is how it looks like through a model. All right, it looks like a picture of a SAM, scanning electron microscope, which is very expensive instrument. Okay, and right now it is a mobile camera picture. Okay, and this is how the model looks like. We have a model for solid in 2 dimension where the spherical ball of steel are about 10,000 in number, placed between 2 parallel plates having a spacing around 1 mm. And when we see through, then we see the dense random packing of hard spheres as a model with a lot of defects in it. The grain boundaries, the vacancies and dislocation are visible throughout the structure. So the solid, it shows a plane, a monatomic plane. So you have seen the vacancies, dislocation, okay? All these are visible here. We have a model for normally solid in these 2 are dimension. All quantum phenomena, which you see from the expensive instruments, okay? But
Very
with
true,
the
sir,
low-cost things, you can see that. In order to show the van der Waals potential, This is how we represent in a classroom van der Waals potential. This is a repulsive, and this portion is a attractive. Okay, and this is the equilibrium distance. All right. So this comes through this model. You have a bar pendulum. We have a small bar pendulum in which there is a gravitational force of attraction at the center, but there is a repulsive force of magnetic interaction that results into a van der Waals configuration, and it comes in equilibrium at certain distance. When you release it, it never comes to the center. Because the gravitational force is bringing it towards the center, but the magnetic interaction is taking it away from the center. Right? So this is the configuration. Okay. And if you have the two magnets at the bottom, you can modify it. Van der Waals potential is found in crystals. In order to represent that, we have an oscillating magnet between two permanent magnets. So sometimes it finds the kinetic energy is not enough to cross the potential barrier, then it is trapped close to one of the magnets. It can be trapped in a magnet, one magnet, or another magnet. Two magnets. Okay, shows a bound electron, and once it is has enough energy, it shows a continuous. We have a small bar like single atom. These are the energy levels, or how the electron is there moving around the nucleus. For two atoms, the energy level are shifted like this. Okay, this is what we teach. All right, and through that model, we are describing that. Okay, so all these quantum phenomena, we are having analogous mechanical model, and the parameters are within the visible range. Okay, let me show you the magnetic potential. One. Oh, okay. Like this. Van der Waals potential is found in crystals. In order to like represent that, we have which can go oscillating to any atom between but when the energy is smaller magnets. So sometimes it finds the kinetic energy is not enough. This is like a bound electron to cross the potential barrier. Then it is trapped close to one of the magnets. It can be trapped in a magnet, one magnet, or so the another idea magnet. Is your bookish picture of quantum energy levels, you translate into mechanical model and bring the parameter so that they are in the visible range. Okay. For example, molecules when they are coupled. So here, these are the ring magnets. Okay, which you can suspend and see it, what is happening, and see the dynamic behavior. When you disturb anyone, there is an interaction at the other. Okay, so the atoms are also behaving exactly same way. If you disturb one atom, the other atom gets disturbed. They don't touch each other. Okay, and this is how the communication, energy transfer, even the sound propagation takes place. Okay, if you have a series of these atoms, then you can have like Newton's cradle. This is a Newton's cradle, magnetic Newton's cradle. That is what is the innovation. If you disturb one, the disturbance goes to the last. This is your mechanical analog. This is mechanical analog. Okay. In mechanical analog, if you disturb one, then hits the last one. If you disturb the 2, then it takes away the last 2. Okay. And this is a magnetic Newton's cradle. When you talk about the anharmonic oscillator, normally in the laboratory you teach only the harmonic oscillator, no anharmonic oscillator.
We have modified a bar pendulum in which the restoring force is due to gravity as well as the magnetic interaction. At the bottom of the bar, we have a magnet oscillating with respect to a fixed magnet on the table. The resultant motion is that it is an anharmonic oscillator because the restoring force
is no more linear. The magnetic interaction also comes, which is 1 by r square. So it's a combined effect of these two. So it becomes a non-linear restoring force, and the motion is anharmonic. When you see the energy is not enough, it is unable to cross the barrier. So you get a concept of a potential barrier. Okay. So these concepts, for example, here, this is a magnetic oscillator altogether.
We have got a bar pendulum with strong attractive magnetic interaction at the bottom, shows a very good character of a harmonic oscillator. When the amplitude of oscillation is large, the time period is also large, but as the amplitude reduces, the time period also decreases very rapidly. It shows
what I showed you earlier is this potential valve. This potential valve. Okay. This is very narrow here. All right. So the frequency is higher, the energy is also higher. And here the frequency is low. The energy is also, well, in fact, reciprocal, okay, with respect to nucleus. All right. So this sort of a potential, can you imagine how it exists with the nucleus and electron? So it can be represented in the form of magnetic oscillator. This is a magnetic oscillator. Okay. If you disturb this initially, so there is a large amplitude.
In this model,
and the frequency is also
bar pendulum
low.
With strong attractive magnetic interaction at the bottom, shows a very good character of a harmonic oscillator. When the amplitude of oscillation is large, the time period is also large, but as the amplitude reduces, the time period also decreases very rapidly. It should
well, we can talk about the resonance also in these magnetic systems, okay? Because resonance is also a quantum phenomenon, all right? So in magnetic systems, you need to have a coil in which you can feed the signal and you can have an equilibrium on these magnets, repulsive magnets, okay? And this is how the dynamic picture looks like. Okay, at a particular frequency of input signal, this will have a maximum amplitude of vibration. Okay, when you change the mass, then the frequency changes. All right, so it's like bound states. Okay. And you can have the configuration in which the middle magnet vibrates or the top magnet vibrates. Okay, these are called the modes of vibration. All right, so at different frequency, you are having a configuration that this magnet doesn't vibrate. So this is a free end which is vibrating at a particular frequency. But at other frequency, this middle one is vibrating. This is stationary, the bottom is also stationary. Okay, so such quantum phenomena, internal vibration, external vibration, can be bought in the visible range. Okay, so that has been the theme of all these development. like this Raman effect. Again, we can talk about the mechanical model. And this is how the mechanical model looks like. We have the interaction between this pendulum and this oscillator. Okay, this pendulum is moving like this. Okay, and this oscillator is a spring mass oscillator. But this oscillator has got a magnet, and this has also got a magnet. Okay, so when a photon it is interacting with the atom, so that's how the analogy is. This is an independent oscillator, and they can interact in phase or out of phase, depending upon the energy is a stock or anti-stock transition. Okay, you can see it again. This is an independent oscillator, and this is a moving photon light. So photon can interact with the atom depending upon whether the electron is moving towards the photon or moving away from the photon. Okay, because electron has a dynamic picture in an atom. So in phase and out of phase, that concept comes in. All right, and you can illustrate. This is a mechanical model of a Raman effect. All right, this is, for example, Bohr orbital. Bohr orbital at low frequency is set up. Okay, a circular loop is mounted on a speaker, and speaker is connected to a signal generator. So you can vary the frequency. Here the R radius of curvature is constant. Okay, so you see the node and antinode along this loop, which is analogous to the Bohr orbital, the quantization condition. And the quantization condition says that 2 pi r equal to n lambda, where n is the frequency. Okay, so such situation you can have when you excite this speaker with the signal generator. Then you observe the node and antinode along this loop. Okay, and as you vary the frequency, at other frequency you can have large different number of loops within that. Okay, this is another mechanical model on the same theme, Bohr orbital, and you can really visualize. Okay, this model has got a reference of American Journal of Physics. This has been published. Okay, they appreciated that at such a low frequency also you can observe the wave phenomena inside this loop. Can you see a collective motion of this loop? This is analogous to the 2 pi r equal to n lambda condition, because n is this one. Okay, this is really a low frequency domain development.
If somebody does not have the requisite space to set up the entire innovation hub, is it then possible to take few experiments only because of space crunch?
Space crunch, we recommend don't go below 10, because then you don't appreciate. Okay, so 10 or 20 or 30 you can plan out. Okay,
because sir, these concepts are very much required during the undergraduate modern physics courses.
yes.
So I think because of space crunch, everybody may not be able to give out that much space.
Give out the hall. Okay.
But we would indeed start a dialogue on whether some experiments can be accommodated within the available space, and when space expands, we can take something further.
Yeah, space and of course money.
Yeah, in phased manner,
we can only 10. Yeah.
Yes,
we can do that. Okay.
These are amazing experiments, sir. We spend so much of time making the students visualize this, and it's amazing. Sir, please provide us the reference of that American Physics Journal where this is explained in detail. Thank you so
much. This is on a frictionless air track, as I explained to you. Okay, and this is how the dynamic modification looks like. Okay, for example, a moving magnet is oscillating between the oscillating magnets. So here it's a variable field. So sometimes the interaction is in phase or sometimes out of phase. Okay, so the concept of phase comes in. So in a phase, okay, the energy of the oscillator increases, and in out of phase it decreases. Okay, so as I explained in the form of pendulums, okay, independent oscillator, here it is a linear motion like alpha particle traveling in a medium. So it can be trapped or detrapped depending upon the oscillatory field along with the gas available. So you will be able to observe that here, the trapping and detrapping, okay, at a particular condition. Just wait, because this video is about 3 minutes long. Okay, in the next transition probably it may be trapped. Now it is trapped and then detrapped. Okay, so your vocabulary is visible, whatever you are saying. Okay, it's a happening, and that gives you a different feel altogether for a learner. You see, it escapes. There's no trapping. Okay? So it's all probability game. You have to set up the experiment, do it patiently, and make a recording. Because all these mechanical systems are classical. There's no quantum in these. But the concepts which are there in quantum, those are coming in the visible range. Well, something on the molecular vibration, for example, this is a model of a water molecule, H2O. Okay, the oxygen and two hydrogen atom. This is all mechanical model. Some springs are used to attach plastic balls. Okay, and this water molecule is kept on speaker now. Okay, and again it is connected to the signal generator. So you can tune the frequency and find out what is the frequency at which resonance takes place. So you see the resonance. This is the resonance. And this shows, this is the mode of vibration of two hydrogen atoms with respect to oxygen. So these are called torsional mode of vibration. But at other frequency, this is the mode of vibration at higher frequency. So we call it as a stretching mode of vibration. All right. The bonds are stretching or they are twisting. So these are two different modes of vibration, which are having relevance in quantum science. Because when you study the NMR, you get peaks at two different frequencies. And then how do you correlate? You never visualize. Okay. Through such model, you visualize. Okay. The same thing, you can use it for methane molecule. These are only the ideas, okay, which we are floating with the next generation. So there is enough scope. They can build any molecule using this mechanical model. Okay, mount it on a speaker. So whatever he has learned is to vibration analysis of the system. Okay, using the speaker and a signal generator. So these things are already there in the laboratory. But to use it in an altogether different way, so that perspective is important in pedagogy. Okay, so how you can use it to understand the quantum phenomena, which you learn in an altogether different way. Okay, either mathematically or using some hand-waving argument or illustrations. All right, the illustrations is also coming from some intelligent minds, you know, but these visual impact is so powerful that anybody who has not learned any mathematics or not learned any quantum science, they can appreciate. Okay, like this is the torsional mode of vibration. All these balls are shaking, you know, at a particular frequency. All right, and the same model at different frequency shows the stretching mode. Okay,
और आगे पीछे भी होते हुए दिख रहे हैं.
okay. So such observations are unique observation. They can come only through such independent place. In a conventional layer, they are not available. Okay, so you have to think innovatively how to modify the lab and introduce these concepts. All right. Well, Rutherford scattering, again a ring magnet and a bar magnet is used. So this is a conceptual Rutherford scattering. You are having a back scattering alpha particle from the nucleus. Okay, and it follows 1 by r square law, q1 q2 by r square. So the fundamental interaction is here, it is Coulombian, q1 q2 by r square, but for mechanical model it's a magnetic interaction. Okay, that's the only difference. In place of having this size effect of alpha particle and nucleus, you are having ring magnets. Okay, so the behavior is also same. It follows the trajectory as shown here. This is the trajectory, and this scattering angle is measurable using a circular dial. When you throw the pendulum repeatedly, you can reproduce. You can reproduce the angle of scattering. You can also change the impact parameter by changing the position of this ring. Okay, you can change the kinetic energy by shifting this release mechanism at different distances. So more kinetic energy can be required. So the quantum Rutherford experiment, okay, which is not taught or not done anywhere in undergraduate colleges, but it is taught. Okay, but these mechanical models can stay there. Okay, to visualize those concepts. Okay, like the plasma, we say fourth state of matter, and that's all. All right, but how do you realize it in the laboratory? That is important. So as I showed you, this is a small chamber. In a small chamber, 2 electrodes are mounted. These are all metallic wires hanging, and through this spark plug, high voltage is connected. So when you apply high voltage, the gas normally doesn't ionize. Okay, only at low pressure, the gas can be ionized. Okay, so you have to reduce the chamber pressure by evacuation.
We have a small vacuum chamber about 2 liters, in which we have got 3 electrodes where we can apply some biasing. And to the electrode, one straight wire is connected of iron and another a ring electrode is connected. Once there is air, there is no flow of current when biasing is there. When we remove air, suddenly the gas discharge starts and we get a very nice plasma across the electrodes. Across the negative electrode, where the ions are collected, we get more density of the plasma. Across the positive electrode, where the electrons are collected, there is no much illumination.
So, I mean, whatever you are teaching, right, that goes with the experiment. When you are doing vacuum, means removing part of the air, so that even when the ionization takes place, you are allowing them to move freely. There is not much recombination and so on. Okay, so whatever plasma is confined there, and you can see the light coming from the plasma. Illumination is coming from the plasma. Bouncing laser beam. Well, this is also one of the interest. Normally, the laser beam travels in a straight line. Okay, can you see this laser beam? It travels in a straight line.
Yes, sir.
Even in water, it travels in a straight line. Okay, but if you have got a sugar solution, okay, you can vary the density. If you have a pot in which you add sugar, so there will be a concentration gradient. Like in atmosphere, the atmosphere is very dense, close to the Earth's surface, and it is rare and rare when you go up. So this sort of a density gradient you can generate in the water tub. And this video shows that. So you are having a concentrated solution added at the bottom. So here it's a very little sugar at the top. So the laser beam goes straight. But as you take the laser beam down, okay, because of the concentration gradient, it deviates from the path and you see the bouncing light.
So again, scoop per le jao.
Okay.
Then downward.
All right. So the nonlinear path is because of the graded density, variation in the density. And that's why along with the horizon, even when sun sets, it's visible. Okay. And we say because of the curvature of the earth, the light gets bent and it reaches. It's not. It's because of the variation in the refractive index. Okay. Well, such phenomena which are visible in the range, okay, you learn many things with the toys, right? So this toy is available in the market. What you have added is only table tennis ball, like ears, okay, and mounted on a speaker, and you want to see the resonance states, you just tune the frequency, okay, and this is how it says, enjoy. All right, at a particular frequency. When you change the frequency, all right, you can tune such a mode, kuch nahi samajh mein aaya. All that was bakwas. Okay, but few of them will say yes, kuch to samajh mein aaya. Okay. So you have to tune the frequency and excite different modes of vibration. I call it as modes of vibration. Okay. Or for toy, it's a mood. So it's a no is one of the mood and yes is another mood. Okay. And of course, when you are really excited, well, you like to clap. Okay. If you enjoyed the journey of Innovation Hub and the quantum science brought to you in the visible range. Okay. And well, I like to stop here. We have developed several, so abhi 50-60 kareeb hain, different model. Any 20, 10, 30 aap manga sakte ho. ठीक है? And we are ready to share. Set up a science gallery. Okay, this is the dream what most of the teachers have. और ये साइंस गैलरी उनके पास ही होनी चाहिए, अपनी इंस्टीट्यूशन में, अपने काबू में रहनी चाहिए, so that whenever we are excited, we can take our children there to share the science whatever we are teaching. Okay, तो इस तरह की इनोवेशन हब जो प्रोमिनेंट पीलीभीत उत्तराखंड में लगा रखी है, and they are really excited to have this innovation hub. They are using it for marketing.
There is a common notion that physics is incomprehensible to the people of average ability. If you think so, please visit the Benher's Innovation Hub. Here you can readily and eagerly learn the laws of physics with the help of ingenious models designed by the most dynamic, passionate and outstanding personality, Professor Y.K. Vijay, Director, Center for Innovation in Science Teaching, the IIS University, Jaipur. This Innovation Hub was inaugurated today by Honorable Mrs. Ranjit Kaur Sehmi Ma'am, Founder Principal, Benher Public School, Pilibhit. Here you can easily understand the concept of electromagnetic induction, eddy current, laser diffraction, Doppler effect, rotational dynamics, plasma state, Bohr's orbit, wave formation, and many more. So please take out the time from your busy schedule to explore our newly inaugurated Innovation Hub, the only one in this Pilibhit area. Thank you.
There is another one in Uttarakhand at Rudrapur. This is a DPS, again, Delhi Public School.
Science is simply common sense at its best. It is a common notion that the concepts of physics are difficult to understand theoretically. Everything is theoretically impossible until it is done. If you feel the same way, please come and visit the exciting Innovation Hub of Delhi Public School, Rudrapur, where you can understand the typical concepts of physics by performing hands-on activities with the help of amazing models designed by the most dynamic, passionate and outstanding personality, Professor Y.K. Vijay, President, Indian Association of Physics Teachers, Rajasthan. This Innovation Hub was formally inaugurated by Dr. C. Tiwari, Director, V. Chandra Singh, Garhwali, Uttarakhand University, in presence of Professor Y.K. Vijay, Chairman of DPS Rudrapur, Shri Surjit Singh Grover, Principal, staff and students. Here you can easily understand the concepts of electromagnetic induction, air cannon, Doppler effect, diffraction, eddy currents, vitricity and many more. Why don't you take some time off from your busy schedule and visit the Innovation Hub at DPS Rudrapur to discover a lot more about the world of science.
Sir, we can happily say that we are feeling a little bit jealous. The schools are investing more into the understanding of physics of the students. And I think through this wonderful webinar supported financially by NASI and completely supported in spirit and also helped by IAPT and your good self, I think all the teachers involved from different Delhi University colleges should think that this is a particular possibility to set up within their colleges so that it is really beneficial to the whole learning society in reality. And then what is there is what I find is that people are or institutes are investing more into things which are not really enhancing the knowledge and learning system of our teacher learner or student learning and teacher learning system, rather than they are investing somewhere else. I mean, it's very evident even if to impress NAC and get credits and so on. I think the real appreciation would come if we would have an innovation hub in each college, because as you said, even though we are in Delhi and the National Science Center is there within New Delhi, we cannot each semester take out time to take all the students there. There are so many of them, it is not possible. So these experiments within your college would be extremely interesting, and I don't have words today to thank you, sir. I don't think there is any word available.
You should collaborate with NASI for this sort of a project, that this sort of innovation hub should reach all the institutions, because the NASI's mandate is also something like that, to spread the knowledge, in an effective way. Even in the new education policy, there's a lot of mandate on skill and hands-on.
Yes,
so
exactly.
Countrywide, we are talking about.
Yes, but we
how
are not
to make an
doing
effort?
it. Yes. Instead, we are having those prescribed experiments, which unfortunately the vendors are progressively providing only in simple box in a box. So the student hardly knows what is inside. The student is only connecting some wires and is not able to develop. What do you think, Dr.
IIPT's, perhaps what I feel is IIPT's major contribution is this openness, to share with others, right? Because mostly all these models we share at different platforms, and even I'm learning from different people. What I'm doing, I'm integrating these concepts, and sharing with the next generation. That's all. So if you take an initiative, take few, and then add on your own ideas, and then it grows, it multiplies. Okay. And that is what we are looking forward to. So we should start some chain reaction this way. So at least teachers are motivated, take few models from here, add on their own ideas, and then innovation can be generated rather than procured. Okay.
Dr.
Actually,
Bindal,
we
please.
see, actually, sir, in NEP syllabus, I mean, we have only limited syllabus available to us right now. But even in those
Okay.
labs, we are being asked to do innovations in the standard experiments. So, you know, we get a
Yes,
clue from
correct.
here how to go about it. So it is
How to go.
very interesting and very fruitful as such for
Yeah.
the academic community. It was an excellent talk, excellent presentation. We actually saw those experiments. It was so very inspiring. Thank you so much.
Good. Thank you.
Would any faculty,
hopefully when the
yes,
opportunity comes,
Yeah,
okay, try to visit physically
Yes,
somewhere.
definitely.
Dr. Pathak wants to say something. Yeah, please, Dr. Pathak, please.
yeah. Not only this innovation hub, when I was the head of the department here in Gurukul Kangri University, I have done, constructed many experiments of MSc level in such a way of this innovation hub, so that the students come out of the boxes and they can visualize all the experiments like this. So I have already done here in the Gurukul Kangri University.
Yeah, doing themselves. Yes.
Even MSc students, MSc experiments they have done like that, so that they can see. For example, from this professor, क्या नाम है, जो नासी के वो हैं, IIT कानपुर के जो थे ना, क्या नाम उनका,
वर्मा, S.C. Verma.
Verma ji came twice or thrice to our university, and taking inspiration from him, have converted many experiments, MSc experiments like this, so that the students can see them, how these things, say for BSc, even BH Karo, and many others like this. So maximum of about 80% of the experiments I have converted, even of MSc level, to such experiments like this, so they can see it.
They can see it. Okay.
For others, it is all right to have this your innovation hub also, but I have already converted when I was head of the department there in.
Professor Pathak, I think I would make a request, since everything is on digital platform nowadays, so that it is accessible to the masses. So maybe if you have done so much of, you know, contribution to this, maybe if it is possible, then make it available to people. I mean, they would get inspired and they would also try to do something similar. So
I think
we should be
now
able to reach out to that.
I will try, but I think now, because I am retired from the institute, so it may be little difficult. I'll consult.
Sir, which institute may I just missed it because of coordination? Which institute, sir?
Gurukul Kangri University, Haridwar.
Gurukul Kangri University, Haridwar. So we can arrange that you have to only say, and the entire filming will be done. That we can arrange somehow. That we can arrange. You are there to explain, and then we will film the whole thing within your university or institute, and then it will be beneficial to everybody.
Right. Yes.
Sir, please send us your email address separately, so that within the chat box or in the webinar list, wherever you are connected with us, and we'll surely manage it in the near future.
Okay.
I hope
And
so.
we have to take the permission of the head of the department presently.
Yes, sir, we will follow the due procedure, but I think, I mean, as I said to Professor Vijay also, I'm feeling jealous. Why don't we have it here in Delhi?
Actually, this came to me when some students or some even grown up say, I was sitting at some airport and somebody asked, what are you doing? I said, I am professor of physics. Oh, physics is very tough subject. Physics is very subject. So I said, this is not because of you, but because of us teachers, which are not doing it properly. if you are just only deriving the things on blackboard, that will be living tough. But if you can see the things, then only it is interesting.
Correct. So
Sir, can you
seeing is
please,
believing.
sir,
You
can
know,
you please
seeing is believing.
repeat your email ID? Everybody is asking. I'll just type on the chat box.
Okay, it's a Vijay YK
Vijay YK.
@gmail.com.
Oh, very simple. And sir, Patak sir, would you also repeat your email ID or?
Yeah, I will do it. Okay, this is
Vijay sir, can you please see I've typed correctly vijayYK@gmail.com.
Correct.
Yeah, exactly. Everybody has been asking for your email ID.
देखिए, आपने इस तरह का कहीं देखा है क्या?
Sir, what is this? This is a bottle.
बोतल के अंदर बोतल, पानी की बोतल है, ठीक है, और बोतल के अंदर एक बोतल है.
Okay.
हाँ,
Okay.
वो फ्लोट कर रही है, तैर रही है ऊपर, ठीक है, and I just press it, it goes down.
Okay, goes
when
down.
I depress,
we should hold Viva with such experiments, sir. After the experiments are done, we should hold Viva with such models for the students.
I actually see this one like maybe in 2015 or so. At that time, I was teaching in school, and there is a teacher from TGT chemistry, and he made this model for the students. It was back in 2015.
It's a principle of submarine.
Submarine, yeah.
Yeah, how the density changes with the pressure. Okay, so right now the density is low, therefore it is floating. When you press, okay, a little water penetrates inside this bottle, little more water, okay, so that it becomes heavy, it goes down. So inside this bottle, there is the air as well as water, half air and half water. Okay, so the quantity of water you are controlling by pressure. And that's how it works.
Miraj Ahmed writes that he has seen this in Shiksha Sopan by H.C. Verma sir. And that's another forum where you can see such small experiments.
Definitely.
Shiksha Sopan. And there is also one Shiksha Shilpi. There are many initiatives going on throughout our country to let the science students remain in science and not deviate towards other fields.
Correct. So once you have seen it, then you should be possessive. They should be with you. Okay. And that is what you said. You feel jealous, means you don't have it, but you can have it. Okay. Work
yes,
for
sir,
it,
definitely.
You will have it. Okay.
Definitely, sir.
So small effort, take few models from us, and then add on your own ideas.
Yes. Indeed, sir, we shall not let this go waste. We shall definitely make efforts to incorporate 10 experiments at least from Innovation Hub with whatever space we have in our college. And I'm sure many colleges have enough space.
Sure.
They can actually do it, the whole thing. And I
and
now request
that is my mission.
Yes.
That is my mission. It should reach to maximum people as it has come from H.C. Verma. We have inherited many things from H.C. Verma. All right. And now we are distributing all over. All right. The ideas are simple. Once you assimilate, then it becomes yours. Okay.
Yes.
And if it is with you, you are possessive, you can have it and you can share it with your students. Okay. And that's how it should go. Right.
Indeed, sir. That's the real legacy. I now ask formally everybody who is within the meeting to switch on the camera for a minute so that we can have a screenshot of this wonderful session and our remembrance that you all were here with us on this wonderful day. And I think nothing can be better than remembering a day with our colleagues, our students, where we all learned together so many new things. And we take a pledge within ourselves that we will definitely try to imbibe some of these experiments for our students' understanding and keep the interests alive and pass on the legacy. And be innovative.
Be innovative in thinking and sharing. Okay.
Yes, indeed. And pass on the legacy as Professor Vijay has rightly said. Thank you so much, everybody.
Thank
Thank
you.
you so much, sir. We have no words to thank you. Thank you, everybody who has joined together, all the students, all the respected faculty members, my senior colleague, Dr. Bindal, Dr. Rachna, and everybody here, Dr. Varsha, whoever is here, helping me coordinate this event for the benefit of everybody. With those